Okay, so here is the third chapter. The third chapter that we have is on elements, compounds, and mixtures. And we're going to be discussing how each of these differ and how we're going to separate mixtures. So, first of all, what's an element, what's a compound, and what is a mixture? Element is defined as something that contains only one type of atom. Not one atom, it contains one type of atom. So it has many atoms, but all of them are identical. So you can say it contains identical atoms or one type of atom, or all the atoms are the same. Now, in a compound, the compound is made up of what? Two or more elements chemically combined together in a fixed ratio. That is the definition. Two or more elements chemically combined together in a fixed ratio. That means when you look at a compound, all the individual molecules are the same, but each molecule is made up of different elements. So they're all same compound, but each compound is made up of different elements. For example, NaCl is what? NaCl is sodium chloride. It is made up of, each molecule is made up of one sodium atom attached to one chlorine atom, and they have to be in a fixed ratio, one sodium to one chlorine. H2O is water. That means water is made up of one oxygen atom attached to two hydrogen atoms. Sodium carbonate is Na2CO3. This is a compound that is made up of two sodium atoms, one carbon atom, and three oxygen atoms. So a compound is made up of different elements, two or more elements. They have to be chemically combined together in a fixed ratio. You need to memorize definitions, and you need to write them accurately. Sometimes when you try to write them in your own words, that's fine. If it gives the same meaning, that's fine. But in most cases, when you try to put it in your own words or differently or something, you come up with a different meaning, so making the definition wrong. So please, the easiest question that you can have is writing a definition. It asks for a definition, you just write it as it is. Compound, a substance made up of two or more elements chemically combined together in a fixed ratio. Now, what's a mixture? A mixture is two or more substances added together. So it is something that has different substances. Some of them may be elements, some of them may be compounds, but they are different things added together. So they are two or more substances added together, and these can usually be separated by simple physical processes, or they can be separated easily. If you don't remember simple physical processes, you can just say can be separated easily. Okay. Solutions are examples of mixtures. So a solution is a mixture of two things, one of them dissolved in the other. The one that we dissolve is the solute. So the salt or the sugar that we're adding to the water, the sugar is the solute, and the water that we're using to dissolve it is the solvent. So the solute is the substance that dissolves in a solvent. The solvent is the substance in which a solute is dissolved. So let's look at some questions. Which of these is the formula for a molecule of an element? So which of these is an element? But he's asking for a molecule. Do you understand the difference between molecule and element? So answer A gives you just H. H is just the symbol of the atom. It's not a molecule. Hydrogen is one of the things that has a molecule made up of two atoms. So actually your answer should be B, because that is the molecule of an element. Of course, C and D are wrong, because C and D are not elements in the first place, right? They are made up of two different atoms, two different types of atoms, so they're not elements, they are what? They're compounds. Which of these is a mixture? Sodium, chlorine, sodium chloride, or sodium chloride solution? Remember, if I have something containing only sodium, that's an element. Something containing only chlorine, that's an element. Something containing only sodium chloride is a what? It's a compound. But if I have sodium chloride solution, that means sodium chloride dissolved in water, that is a mixture. Can you see that X? Okay. Pure substance is something that contains no impurities, so it contains only the substance alone, nothing added to it. A pure solid would have a fixed sharp melting point. A pure liquid would have a fixed sharp boiling point. So if I have something that is pure, it will have a specific melting point. At a certain temperature it will melt, or at a certain temperature it will boil. So in order to know if a solid is pure, I test its melting point. If its melting point is fixed and sharp, it's pure. So what if it's not pure? If it is not pure, then it will melt slowly over a range, and it will have a melting point different from the one that is for a pure one. If we're talking about a melting point, the presence of impurities causes the substance to melt at a lower melting point. So if something melts at 0, for example, ice melts at 0. Now, if I add some salt to the ice, it will melt at what? It will melt at, for example, -1, -2, slightly lower. Not too much lower, not at -20 or something, but it will melt at a slightly lower melting point, and it will melt over a range. That means it will not have a fixed, sharp melting point. It will melt over a range of temperatures. Presence of impurities in liquid, what would that do to the boiling point? It will cause it to boil at a higher boiling point. So the presence of impurity, if I have a pure water boils at 100. But if I add some salt to this water, it will not boil at 100. It will boil at 101, 102, 103, something like that, slightly higher than the original boiling point. Now, why do we care about this? Because purity of a substance is always needed in our everyday life. For example, when we're talking about food, we need our food to be pure. We don't want impurities in our food. We don't want impurities in our drugs. And please remember, the word drugs here means medicine. The word drugs means medicine. Drinking water also has to be pure. You cannot have any impurities in your drinking water. Okay. Now, the other thing we need to talk about is solubility curves. Solubility curves are curves that are drawn to show what is the solubility of a solid at a certain temperature. For most solids, as you increase the temperature, more and more of it will dissolve. So, for example, if you look at solid A, can you see the graph for solid A? Solid A, as we increase the temperature, the solubility increases. What do we mean by solubility? Solubility is the amount of solid that you can dissolve in a certain amount of water. So in this case, it is how many grams of the solid can I dissolve in 100 grams of water. So as I increase the temperature, I can dissolve more and more of solid A. The same with solid B, but solid B doesn't increase that much as solid A. Now, what about solid C? How is solid C affected as I increase the temperature? Can you see the graph for solid C? It doesn't change. And that means for solid C, the solubility does not change with increasing temperature. So if you look at the solubility curve, you will be required to draw solubility curves, for example, from certain information, and you will be allowed to analyze it or to explain something about it. So for this curve, for example, at 40 degrees centigrade, which solid is more soluble? Look at the temperature. Where is 40? Go up, 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 up. Which one is more soluble at 40? Can you see that it is the graph for B that is more soluble at 40? At high temperatures, solid what is more soluble? So at 90, which one is more soluble? The one that has a higher curve. So solid A is more soluble. Now, which one is not affected by temperature? Temperature does not affect the solubility of which one? We said solid C. It has the same amount dissolving, whether it is at 20 degrees or at 90 degrees. Okay, the maximum, this is another question. The maximum mass of a solid that dissolves in 100 grams of water at a given temperature is called its solubility. So actually this is definition of solubility. Solubility is the maximum mass of a solid that dissolves in 100 grams of water at a given temperature. Because remember we said solubility changes with temperature in most cases. The table gives solubility of a certain compound, potassium nitrate, at 6 different temperatures. Plot the points on the grid and draw a curve of best fit. You know how to plot a graph, don't you? You know that to plot a graph, you should use tiny little x's, not dots. Tiny little x's placed as accurately as you can. So if you sit down and plot this, your curve, your graph should look like this. Tiny little x's where the temperature and the solubility meet. You know how to draw that, right? And then, once you have plotted the points, you cannot leave them like this. You have to join them. Now, to join them, before I join anything, I look at the question. Does he tell me to join it in a specific way? He says, draw a curve of best fit. Then I should draw a curve. A curve is something that you draw with your free hand, not with a ruler. Okay? So your curve should look like this, going through as many, or almost all the points, as near to all the points as possible. Okay? That's a curve of best fit. Now, extend your curve to find the solubility of potassium nitrate at 10. So this was your original curve. So what are we supposed to do? He wants at 10. Where is 10? 10 is way down there. So I need to extend my graph. To extend my graph, I need to extend it in the same way that it's going down. So it should look something like this. Now when I extended it to 10, the solubility is 32. So my solubility is 32 grams per 100 grams of water. Can you see that? Okay. Use your graph to find the maximum mass of potassium nitrate that could dissolve in 50 grams at 35 degrees centigrade. So first of all, he wants at 35. So I look at the graph. Where is 35? 35 is there, and then I go up to the curve, and then I go horizontally, and I find that it meets at 56. Is that my answer? That's not my answer. Because the graph is solubility per 100 grams of water. That means if I have 100 grams of water, it will dissolve 56 grams. But he doesn't have 100 grams of water. He has what? He has 50 grams of water. So 56 dissolves in 100. So how much dissolves in 50 grams of water? So this is a cross multiplication. 56 times 50 over 100, and that means that it will dissolve 28 grams at 35 degrees centigrade. Do we understand what we did? Okay. How do we separate mixtures? Remember the definition. What was the definition of mixtures? Definition of mixtures is substances added together and can be separated easily by simple physical means or simple physical processes. So one simple process of separating mixtures is filtration. Now when do we use filtration? We use filtration if I have an insoluble solid in a liquid. So I have a solid that doesn't dissolve and it is in a liquid and I can filter it. And please know how to draw the label diagram of this apparatus, because you will need to draw the label diagram of this apparatus. Remember that if you have something that's insoluble, like what? Like sand, for example. Sand and water. You pass the mixture through the filter paper. Can you see where the filter paper is? You pass the mixture through the filter paper. Where will the sand remain? The sand will remain in the filter paper that is in the funnel, and the water will go down. Now whatever remains in the filter paper is called residue. So the residue in this case is my sand. The filtrate is whatever goes down into the flask. What goes down into the flask in this case is my water, so my water is the filtrate. Okay? So let's try this question. Compound A is insoluble. and compound B is soluble in water. Describe how the student could separate the mixture to obtain solid A and a solution of B. So I give you a beaker that has A and B together. One of them is soluble, the other is insoluble. So what should you do to separate them? You add water, stir to dissolve compound B, and then you filter through filter paper and funnel to obtain A as a residue and B as filtrate. Okay? Crystallization. To obtain a soluble salt from an aqueous solution. That means I have a solution and I want my solid from it, the solid that was originally dissolved in the water. So I use crystallization to obtain, for example, whatever, potassium nitrate from aqueous potassium nitrate, or sodium chloride from aqueous sodium chloride. So what should we do? We put the solution into an evaporating dish and we heat. So we heat until what? Why are we heating in the first place? We're heating to remove some of the water. When I remove some of the water, the solution formed is called a saturated solution. That means a solution that has a lot of salt but very little water. That is what we call heat to point of crystallization. So when I say heat to point of crystallization, that means I'm going to heat the solution to remove as much water as possible. Once I have reached point of crystallization, I cool it, and once I cool it, it starts to form crystals. In that case, I filter the crystals through filter paper and funnel. The crystals will remain in my filter paper, so dry the crystals between filter papers. How do I know if I have reached point of crystallization? Usually when I heat it, I put a glass rod into the hot solution and remove it. If I have heated it enough, if I have heated it to the point of crystallization, crystals should form on the tip. Okay? And when we heat something to point of crystallization, we said that forms a saturated solution. Saturated solution is one in which no more solid can dissolve at that temperature. So I'm heating it until most of the water has gone off and I have very little water, lots of solid that is dissolved in it. That is called a saturated solution. You cannot dissolve any more solid in it. Okay, let's look at a question. The student used this method to obtain a sample of magnesium sulfate crystals from the solution. He heated the solution in a beaker, dip a glass rod into the hot solution for a few seconds and then remove it. What is he trying to do? He's trying to see if he has reached point of crystallization, right? Now, allow the solution to cool to room temperature and then filter off the crystals and dry them. Why does the student heat the solution? We said we have to heat to point of crystallization. Why? In order to remove some of the water, so that I can remove as much of the water as possible. Now explain why the student dips a glass rod into the heated solution. What is he trying to do? To see if crystals form, to indicate that the solution has been heated to crystallization point. He's trying to find out if we have reached crystallization point or not. Okay. Now, another method of separating mixtures is simple distillation. Now, when do we use simple distillation? Simple distillation is if I have a solution and I want what? I want the solvent, I want the water. So I have aqueous something. Remember that the word aqueous means what? The word aqueous means something dissolved in water, substance dissolved in water. So the word aqueous means dissolved in water. So if I have aqueous sodium chloride, that means I have some sodium chloride dissolved in water. Now what do I want? If I wanted the sodium chloride, I would do what? I would do crystallization as we did before. But now I have my solution. I don't want the sodium chloride, I want the water. So I do simple distillation. Now simple distillation is done in an apparatus that is made up of a flask, a thermometer, a condenser, and some sort of receiver or container, such as a conical flask, and it could be a beaker instead of the conical flask. So what do? We heat the solution, temperature rises in the thermometer. Once it has reached its boiling point, remember that once we reach the boiling point of something that we're heating, the temperature stops rising. So I'm heating this, something dissolved in water. Water boils at what? At 100. The temperature goes up, up, up until it reaches 100 and it stops increasing. At that point, the water will start to boil, evaporate, go through the condenser. As it is going through the condenser, what is happening? The condenser is made up of two tubes inside each other. The tube outside, I'm going to pass cold water through it. The tube inside, this is where the water vapor is going. So the water vapor will go from the flask through that tube inside. The condenser is surrounded by cold water. And can you see the direction of the cold water from the tap? The cold water from the tap is going from the bottom of the condenser to the top of the condenser. This is important in order to cool the vapor efficiently and to make sure that the condenser is filled with water at all times. Okay? So the function of the condenser is what? To cool and condense the vapor. The vapor will condense, change into liquid, and what I collect in the conical flask is the pure water. Are we okay with this? Now, fractional distillation is very similar. Can you see how similar it is? It's very similar to the simple distillation. The only difference is what? The only difference is that long fractionating column. Can you see that? So a fractional distillation is also made up of flask and thermometer and condenser and receiver or beaker, but it also has this long column which we call fractionating column. The fractionating column is filled with little glass beads, so that these little balls inside the fractionating column are actually pieces of glass, or it could be tubes of glass that is inside the fractionating column. What is happening? Basically the same, but what we use fractional distillation for is to separate liquids that have different boiling points. So in this case, I have more than one liquid. In distillation, I have only one liquid, water. But in fractional distillation, I have two liquids. For example, water and ethanol. When I'm heating, the temperature starts to rise in the thermometer until it reaches the boiling point of the one that has a lower boiling point. So if I'm talking about water and ethanol, ethanol has a lower boiling point. So it will go up 20, 30, 40 degrees centigrade, 50, 60, 70. Ethanol boils at 78. Now at 78, the thermometer stops rising. And the ethanol starts to evaporate, goes up the fractionating column, and it goes all the way, because this is the boiling point, goes all the way, goes through the condenser, being cooled and collected in the beaker. The water, if any of the water evaporates, it will cool in the fractionating column and go down again because it hasn't reached its own boiling point. Now, how do I know if all the ethanol has been collected? I will know if all the ethanol has been collected if the temperature in the thermometer starts to rise. So once all the ethanol has been collected, the temperature in the thermometer will start to rise again. Now I'm going above 78, 80, 90, 100. Now once it reaches 100, it has reached the boiling point of water. It stops rising. It stops at 100 and the water starts to boil, evaporate, condense, cool and condense in the condenser. And in this case, I have removed my first beaker and put a second beaker in order to collect my other fraction, which is water. So fraction means a group of liquids collected at a specific temperature. So all the ethanol will be collected in one beaker. That's one fraction. I remove this beaker and I put another beaker in order to collect the second fraction, which is water. Okay. Paper chromatography is another method. Now, paper chromatography is used for what? It is used to determine how many substances in a certain mixture. So, for example, if I have a mixture of dyes, or a mixture of sugars, or a mixture of amino acids, I will put a spot of the sample on a baseline. Can you see where the baseline is? The baseline is the line that I draw in pencil near the bottom of this rectangular chromatography paper. Chromatography paper is actually the same as filter paper. Usually in the lab we use a filter paper. So it's a sort of paper that is adsorbent, like a filter paper. So we call it chromatography paper. We cut it as a rectangle. we draw a baseline in pencil near the bottom of this rectangle. And on this baseline has to be drawn in pencil. Why is it drawn in pencil? It's drawn in pencil because pencil is made of graphite, and graphite is something that does not dissolve in the solvent. So it will not be something that dissolves in the solvent and affects the experiment. So remember that the baseline is drawn in pencil because it doesn't dissolve in the solvent. If I draw it in ink, for example, I cannot draw it in ink. Why? Because ink dissolves in the solvent. It will ruin the whole thing and it will give ink all over the place. Okay, so we draw the baseline in pencil near the bottom of a rectangular chromatography paper. Now put a spot of the sample where I have an X. So put a spot of the sample on the baseline. And then put this paper into a beaker containing a very small amount of the solvent. Can you see the level of the solvent? The level of the solvent has to reach the edge of the paper, but it shouldn't reach the baseline. Why is that? Because if I dip the whole thing into the solvent, everything will just dissolve in the beaker and you'll have all the solvent having color in the beaker. That will ruin everything. We want the solvent to go up slowly in the chromatography paper. As it goes up in the chromatography paper, it will separate the different components in the chromatography paper. And notice that as we go up, it separates into different components along that same line. So there are spots on top of each other at different levels. Now the question is, why are they at different levels? This is a method that separates the components based on what? Based on their solubility in the solvent. So my sample at X was something that had two substances. One of them is more soluble in the solvent than the other, and the solvent is usually water. The one that is more soluble goes up further. The one that is less soluble doesn't go up as much. If something is not soluble at all, it will remain on the baseline. So if at the end you still have a spot at the baseline, that means that spot or that substance does not dissolve in the solvent. Now again, this solvent will have to go up the chromatography paper until it reaches near the top, and then we remove the paper. So where the solvent reached is called the solvent front. Can you see the solvent front? So the solvent front is the place where the chromatography, the solvent has reached. Now, once we reach the solvent, once the solvent reaches the edge of that paper on top, we remove the paper and we leave it to dry. We have, first of all, which solvent are we supposed to have used? If we're talking about ink, so if my spot of sample was ink, or if my spot of sample was a food coloring, something that has to do with food, then these are things that dissolve in water. In that case, I have to specify that my solvent is water. Water when I'm doing chromatography on something that dissolves in water, like ink or a food coloring. Otherwise, usually if we're talking about something strange, he will tell you if it dissolves in water or not. If it dissolves in water, then my solvent is water. If it does not dissolve in water, then which solvent can we use? Usually we use ethanol. Ethanol is something that dissolves most of the substances. So my solvent is, if I cannot use water, then you can suggest another solvent. The other solvent would be ethanol. Now, once I remove the chromatography paper from the beaker, I've done the experiment and I've separated it into colors. Now, if it is something that is already colored, I can see the spots. One of them is, for example, brown and the other is green or something. That's easy. But in some cases, we do chromatography of substances that don't have a color. If the substance is not colored, now which substances are not colored? Amino acids and sugars. If we're talking about glucose, fructose, these are sugars. Or if we're talking about amino acids, these are substances that are not colored. In that case, I will not see any spot. I will remove the chromatography paper, leave it to dry, and then I need to spray it with something that gives it a color. We call it a locating agent. So a locating agent is a substance that gives the spots color to make it visible. Okay, now in this experiment, I used the chromatography just to see how many components. So this sample X had 2 components. Can you see that they have 2 components? But in some cases, I want to know what substance is present. So if I have a sample A, can you see sample A? Sample A went up and made a spot somewhere in the middle. Now, I want to know, is A the same as compound 1 or compound 2 or compound 3? So I put spots of the known compounds next to the spot of my sample. And I do the same thing, put it into a beaker containing a small amount of water or whatever solvent I'm supposed to be using, allow the water to move up the paper. Now, how do I know if the spot is the same as something? If it has the same height. So the spots that go up the same height are the same substances. So obviously, compound A is the same as what? It's the same as compound 1. So A and 1 are the same because they have the same height. Another thing is, instead of saying height, I can say RF value. So RF value is the distance traveled by the spot divided by the distance traveled by the solvent. So if I want to determine the RF value of that red spot of compound 3, I measure with a ruler the distance from the baseline to the middle of that spot. Let's say that's X. And then I measure the distance from the same baseline to the solvent front. That's where the solvent went. So the distance traveled by the spot divided by the distance traveled by the solvent, that is what we call RF value. Okay. So let's look at a question. Which method can be used to separate the dyes in a food coloring? To separate the dyes in a food coloring, of course, that's what we just did, which is chromatography. Okay, that ends our lesson on elements, compounds, and mixtures. Again, once you're ready for the quiz, please send me a note by email or messenger, and I will send you the quiz. Thank you.